What's going on, everybody? This is High Peak Education, and I'd like to perform a calculation of self-inductance, inductors, and energy stored in an inductor. So let's look at this problem. A large research solenoid has a self-inductance of 25.0 henries. A. What induced EMF imposes shutting it off when 100 amperes of current through the solenoid is switched off at 80.0 milliseconds? B. How much energy is stored in the inductor at full current? C. To illustrate the difficulty in shutting this solenoid off in 80.0 milliseconds, calculate the rate in watts that energy must be dissipated in switching off the current. Alright, well, let's go ahead and start with our knowns. Looks like the inductance of this large research solenoid is 25.0 henries. That's quite a large inductance. And we want to know the EMF of this inductor in part A when it has 100 amperes of current. So that's the change in I is equal to 100 amperes, and the change in time is equal to, again, 80 milliseconds. That's going to be 0.0800. Yes, that's seconds. Okay, so let's go ahead and calculate first this EMF of the inductor. So that's going to be approximated as minus L delta I over delta T. I mean, if it was a derivative, it'd be di dt, but I mean, we're sort of assuming some average value. So let's put the numbers in. This is minus 25.0 henries, and the change in current is 100 amperes. Okay, and by the way, the current goes from a maximum value to 0, so final minus initial is a negative, and we divide by 0.0800 seconds. Okay, so let's perform this calculation. So let's go alpha F1 for numerator over denominator fraction stack, minus 25 times minus 100, and we'll divide that by 0.08. So that's a large value, 31,200 rounded to 3 significant digits volts. That's enormous. That's more than 31 kilovolts. Like transmission lines voltage. That's huge. Okay, that takes care of part A. And again, this is a large research solenoid, so it doesn't seem impossible. Okay, how about part B? It says, how much energy is stored in the inductor at full current? Well, this is the potential energy stored in the magnetic field that is stored in an inductor solenoid. That is 1/2 Li squared. And this is I max in this case. So we can put the numbers right in. 1/2 times 25.0 henries times the current of 100 amperes squared. So let's get this value. So we need 0.5 times 25 times 100 squared. Okay, so we should have 125,000 on the nose. That's 3 significant digits. These zeros on the end are insignificant, and that's going to be joules. Again, it's 125 kilojoules. That's a lot of energy. Now part C, it says, how much power does this thing dissipate? Well, power is the same thing as voltage times current. So that's the EMF that it requires to shut this off times the current. So we can just multiply those. So that should just be 31,200 volts times the current of 100 amperes. So I think this is 3.12 times 10 to the 4th, and this is another 10 to the squared, 10 to the second. So this is 3.12 times 10 to the 6th watts. So that's 3.12 megawatts. We're not talking gigawatts, which would be actually gigawatts if we were thinking about Doc Brown and Back to the Future. But this is certainly a very, very large power. Alright, so that's what it takes. Thank you very much for watching this video. Please smash that like button if you enjoy this content. Please subscribe to the channel. To grow the channel, please share this amongst your social network. Thank you for watching High Peak Education. I will see you in the next video.